Good morning, and welcome to this second conference day, ITC 24. We start today with an exciting keynote speech from Steve Ashley. Steve is a corporate vice president at AMD, and his focus is on scalable quality system. Steve has more than 30 years experience in design and product engineering, and is responsible for the last year for a cross-functional team that addresses key quality concern across AMD server products, from development to validation and manufacturing ramp-up, to customer enablement and sustained support and drive corrective actions into the AMD processes, as well as industry standard, research, and vendor collaborations. His additional responsibility includes RAS architecture, design for test, debug IP, and CAD, and on-chip control and data plans for Infinity Fabric. Welcome, Stephen, to the podium.
Thank you. All right, thank you very much. I'm very glad to be here. So my talk is about the future of computing depends on you. And who is you? It's all of you in this room. But I know in the last couple of days you've also had a couple other conversations. One was, hey, we need more junior engineers. We need to kind of get that pipeline of test engineers going. We really do need to do that. And the other is, we talked yesterday, there was a conversation with Ruth Cotter from AMD about diversity. And before I jumped into this, I just wanted to say that what she talked about there is very real. At AMD, I see that. We look at underrepresented groups when we talk about promotions. We look at underrepresented groups in different areas, and we take action with respect to those. And I have the good fortune of also being responsible for our Romania Design Center, which is relatively small. But an interesting fact about it is it's 40% female. And that's due to the leaders being very invested in trying to do everything we can to develop. And a lot of those are also very junior folks, I should also add. Most of those are, when I talk to them, I've been at AMD longer than, how old they are. So it's an interesting group. All right, so the future of computing depends on you. Let's talk a little bit, before I get too much, I thought maybe I'd spend a second about my journey. So one of the first things I ever did at AMD is we were having some problems with our SRAMs, and we couldn't figure out what was going on. We were trying to get into production with these parts. We had this brilliant March 9 algorithm we were very proud of trying to implementing and getting. And to make a long story short, what I ended up finding is that we were doing a great job of exercising the part, totally bad at presenting the failures to the pins so that the tester could actually identify that they were faults. So, that's kind of where my journey started. I then, many years later, going through many other things, was in charge of an SoC program. And at AMD, we had this concept that if you're going to do an SoC, we also want to make sure you really feel the weight of the responsibility of getting that into production. So you were going to follow that part as an SoC director into post-silicon and be in charge of the rest of the engineering organization and get it into production. And I was very fortunate to have a really good team, a lot of good folks. And I usually say that we got it in A0 to production. But there's a dirty little secret in there, and that is that we had already paid for the additional mask cost for an expected A1 or B0. And some of the test folks came up to me and said, hey, we're meeting all our metrics, but we could actually improve the test a little bit if we took advantage of those mask costs. So we did. We actually took the risk, went ahead and made that choice, put them in our risk wafer starts, and it worked out brilliantly. So I was very happy about that. But it's a little secret I usually skip over when I talk about we got A0 to production. But it kind of goes to the point that, test is important. Okay, that's what I was saying. And then briefly in my introduction, Paulo mentioned a little bit about what I've been doing the last few years. And in the last few years, what happened around 2020 is, AMD really started to grow in the server space. That's the time where it really started to take off for us. And as we were doing that, we realized that, a lot of the things we had when we'd done server many years ago, some of those teams had gone and some of that expertise had gone. So we ended up creating a team of folks that I was, in charge of that was really boundaryless, right? We took the idea that, hey, if you're a quality engineer, fine, you're part of the team, but you're a generalist. You're a design engineer, great, but you're a generalist. And we come in and we'd go to whatever the problem was, try and fix it, and then after we fixed it, we try and help whatever group should own that, figure out how to own that, and then make that part of our standard practices, kind of have that corrective action process. So, that's kind of what's, led me to the role that I'm in now, where I get involved in these kind of things. And what I want to talk a little bit about today is, it's been great seeing this, what's happened, but there's still so much more to do. And so much of that depends upon you all. Right? And one of the things, as this collection of people were working together, we would talk about was, first thing is, we need to develop the trust with our customers, right? Get to the point where they trust, that we're able to deliver a quality system. And that's very different when you're delivering, tens of thousands of parts to millions of parts to a single customer, and to even beyond in the industry. And as we started thinking about that and talking with our customers, we realized this is really a bigger issue than this. This is really, we need the public to trust us. If we are going to continue this journey of continuing to have more and more compute everywhere, not only in our phones, but in the clouds, it's a massive explosion, right? And as I mentioned, AMD was growing in that time, but we also saw a massive change in the world, right? That was the pandemic time. That's where people moved to even more compute. We were already using lots of compute. We've moved to more. And now with the AI era, it's even more compute, right? So the way this keeps going is obviously the technology is great, but the only way we're going to continue to do that is we can bring the public along with us. And that's a very critical thing that's very dependent on multiple communities, and you are one of those very vital communities which is required to make that go forward. Now, there was an interesting paper, as we started talking about this, that we all came across, and I've leveraged it a little bit. It's not exactly here, from Microsoft back in the early 2000s that talked about this, and it's still relevant today, right? How are we going to maintain the public trust? We got to have security. We got to have privacy. They got to believe in the integrity of the companies and the people delivering this compute. And then we need to have reliability, availability, and serviceability. Right? And we'll talk about how test fits into all this in just a second. And we're really going to talk about the RAS piece and the test piece. So first, I know this is a test community. You all are probably familiar with RAS, but I thought I'd take just a moment to talk a little bit about what RAS is. And RAS has two fundamental goals. The first goal is we want to deliver a high-quality experience to the end customer. That's what we want to do. And there's multiple ways to do that. First, as you kind of heard yesterday in a couple of conversations that I listened into, you need to have the operation do what it's expected to do. Second, you don't want a lot of interrupts, right? When you're trying to do something, you don't want to be interrupted while you're trying to actually do that task. And then you also want the compute to be available all the time, right? You really just want it to be there whenever you need it, and you don't want to have it down. The other thing, major goal with RAS, is you want it to be low overhead to customers. You don't want people to, when they need to have a failure and they want to understand what it is, they don't want to have lots and lots of complicated firmware and tests to try and understand. They want to be able to diagnose very fast. They want to understand, okay, what went wrong? How do I fix that fast? Do I take the part out? Can I reboot it and just get going? They want to move fast on that. And they want all of this to be simple to deploy, not complicated. So how does that intersect test? Well, I think that the way we're going to succeed with this high-quality experience to the end customer is when you overlap three major architectures. It's the RAS architecture, the test architecture, and the debug architecture. I'm going to talk a little bit about each of these. So this is a very simple picture of what happens starting, once you've done manufacturing, and you're doing wafer test, your package test, but then it goes out to your customers, and various customers have different processes they go through to get their customer acceptance test, but then the part's in service. And once you do that, hopefully it stays in service. Occasionally they do take it out to upload software, so it does come out of service for various reasons, but sometimes a part fails and they have to diagnose that. And once you say it's okay to return service, it returns to service, and in some cases you can't, you have to actually continue on to root cause. And generally the way to think about this, there's three major architectures that split across these phases. The first is test, which is what you all are very familiar with. Test, is really kind of what we do at the beginning part here. We really depend on that RAS architecture. Once it gets into those customer acceptance tests, there is some things equivalent to some of the system level tests that we do help with customer acceptance tests. But first order, it's that RAS architecture that's used in service. In service. How do we keep the part up? And then once you get into that diagnosing, the RAS architecture plays a big piece. But you also need a debug architecture. Your debug architecture is once you actually are trying to debug understanding what failed, a lot of times you got to lean heavily into that debug architecture. All right, I'm going to spend a second more on RAS just because I think this might be a little bit new to some of you here, and I think it's important to have this cross-understanding because these things, in my opinion, they all work together, and that's how we end up with a high-quality experience. So just talk for a second about what reliability is. Right? So reliability, these are things like your SRAMs. Your SRAMs on your chip or whatever RAM array, latch array structure you have, is it covered with some kind of ECC or parity? Right? Memory itself, DRAM, has errors in it. We know this. It has errors for a couple of reasons. One, there's manufacturing errors we got to work around. There are also, there'll be soft errors that will happen out in the field, and DRAM's highly susceptible to those. But then also, if you look at the data rates now we have of those DRAMs and those link interfaces, and then also all other high-speed links that we have, those are not perfect systems, right? We do a lot of work, a lot of margining and testing, but there's a statistical possibility that those are going to fail, right? But that reliability is what this architecture tries to do, is try to keep that up and achieve those goals about maximum uptime, minimum interrupts. But it's not zero. All right, the other thing is availability. So what is availability? Availability, the first one's a great example of this, right? When you want to plug a card into your board, preferably you don't have to take the system down. That's hot plug capability. That means your system's still available the whole time, right? If you have an error somewhere in your memory, can you just poison that page? Basically say, don't use that page anymore. Do something with the OS and such to allow yourself to keep operating. And then if it does go down, how do you recover from that quickly, right? So if you have a fatal error and the part needs to recover, how does it recover? What's that interaction with the software to understand what was the failure and quickly restart that part? And then the last thing is serviceability, which gets into some of the things that definitely overlap with the group here, right? The test is, right, once the part actually fails, can you identify what part, if it was not, in our case, like the CPU or the GPU and it was the memory, can you identify which DIMM it was? Or can you, once you start having an error, whether it's on chip or off chip or on another chip, what kind of error testing can you inject and then diagnose and figure out where the fault is? And then other things, just indicators. When you boot a part up, what information you have, what kind of on-chip self-repair. These are all serviceability things. So I just wanted to kind of quickly step through that so you all have a sense of kind of what RAS is. And hopefully, one of the things I think is important, and one of the reasons I mentioned this, is this intersects with test, right? I think hopefully that's clear, right? Some of these things are test functions, some of these things are debug functions, and these things all have to go together to have a complete system. And I drew an earlier picture that showed, hey, these phases overlap, but honestly, I think these things, they extend, and we see this in many of these areas. Right? I talked about a couple of these. But we are seeing more and more the case where these architectures need to go across these entire phases. We might use them to different degrees, but they're all still critically important. Debugging at any phase is important, because once you have a fail, you got to do something about it, right? And in some cases, you can't run tests the way you would, but that's where your RAS architecture comes into place. Where your RAS architecture then goes in and says, okay, there's a failure here, and what breadcrumbs existed, so you can then go in and debug what that issue was, or take some corrective action with your firmware and software. All right, so I'm going to shift gears a little bit. I'm going to talk a little bit about the different phases and talk about, as much as I can, about each of those different areas and how they, both the RAS, test, and debug, and talk about the various phases of the life cycle. Because the life cycle is very important, and to have a quality solution, you need to think about all of these, not just one of these, but all of these. All right, so the first one I'm going to talk a little bit about is the definition phase. And one thing I would like you all to think a little about, and I'll come back to in a second, is I often like to ask my engineers how much we need to improve productivity every year. And then sometimes I'll also ask, how much do we need to improve quality every year? What's that quality improvement metric we need to achieve every year? So think about that for a minute. So in this first phase, we're defining the products. And you got to look at the new technologies that are there. You got to look at research, look at standards. And I'm going to try and hit on a little bit of each of these for each of the fields I just talked about. All right, and the first thing is just to kind of level set on the requirements here. All right, we have seen that SOCs are not scaling the way Moore's Law was many years ago. And that first chart there shows, the relative, transistors you have on a die, similar sized die, over time. It's slowing down. We're not getting the same density we used to have. And the other thing is, as we go into these newer technologies, they're also costing more. So the silicon itself costs more. So these are not, these are trends that, make our life a little bit difficult. But some of we've come up with great ideas to work around these, though. AMD was one of the first to get into the chiplets, right, with our Rome products many years ago. And chiplets really help that. You're able to put more silicon down. You're basically getting more silicon into the package, and that's actually allowing us to go faster than Moore's Law. And then if you also think about this in a different context, the amount of compute needed for AI also is a different kind of transition, right? We used to think of things, working in a certain, in your handheld or your computer or in a server, but now these training things run on multiple racks. All right, but chiplets did introduce some challenges for us, right? Thermals and power is one of the worst, right? We end up with situations where sometimes you're thinning those die, or starting with very thin die, and that really changes your thermal characteristics and how to get that heat out. We've had trouble with even probing these parts now. The bond sites are just so small. And then also, if you're stacking chips, there's just, the architects love this. All these wires we can just put there, but that's really not easy from a test perspective. Put these chips together, stack them, and just, all those hundreds of thousands of wires. And in the future, I believe it even be more than that. And then I talked a little bit about before, but the speed at which we're operating now is incredible, right? It's, we're talking, on these chips, gigahertz. We're talking even faster on the IOs. And that makes us more susceptible to small delay faults. And this is an area that we have actually debugged a fair number of parts that have these. The exact extent of this is a very good question to answer. But we have seen these, and as you go faster and faster, the impact of these small delay defects becomes an outsized proportion of the period of time. So it's an important area we have to continue to research and understand. It makes rework near impossible. And then the other thing is, in the chiplets, if you put all these things together in a package, you really want them all to be good, right? You don't want to put them all together and have one of those things fail, because that's a very expensive proposition. So what can we do about this? All right, so the first thing is try and address that last problem, right? What can we do with advanced fault models, right, to get higher coverage, get closer to that known good die? What can we do with functional test, right? We've found over years of experience that structural tests are great, but they don't quite cover everything. So how do we bring some of that functional testing back into wafer sort? We need standards, right? One of the standards that hopefully many of you are involved in is how do we get this interconnect BIST and repair? How do we get that as to a standard? And there'll be more that we need to do. And then there's so much on these things, we can't try and test through a small spigot, right? That's got to be a really wide spigot so that we can get very fast, get all the scan information we need, whatever debug information, it can move fast, and we can actually use that for quicker diagnosis. And then the other thing is we really need to think about, are we thinking enough about when we test? Is test just at the beginning, right? Or do we need to continue? And we do some of this when a part restarts. A lot of things will rerun the BIST. But do we need to be doing more testing through the life cycle of a part? All right, so I'm going to shift gears a little bit. So that's about test. Some of the chiplet challenges, what I suspect many of you are familiar with. But let me talk a little bit about the reliability architecture and the debug architecture and the couple primary challenges that they have. On the reliability architecture, the biggest one is to understand how to handle these small delay faults, right? And how to do it in a manner that isn't just putting down lots of hardware and not understanding the return on that. So I'll talk a little bit more about this in a minute, but trying to come up with a quantification, a way to rationalize about this so we can figure out when to use the techniques which we know about. You know, there's multiple techniques we can use to address these problems, but we need to know when to use them and how extensively to use them. That's the fundamental problem we have to solve. On the debug architecture, yes, it's very complicated to understand what data we need to capture, and I think that's a whole, you know, realm of opportunity is, hey, you know, it's not just the part fails, but how do we have the information? Did the actual failure, you know, happen millions of cycles earlier? You know, and we can't keep all that data for all those millions of cycles. How do we get that data, and how do we understand what to capture at what time through causes? But the bigger challenge is really going to be data. How do we keep data secure, right? And how do we keep it private? And that's not something we're going to talk about here, but I believe that is the biggest challenge for the debug as we go forward, right? Because, you know, when you have, you know, millions of parts in a fleet, you know, we're going to want to help diagnose those. But to do that, you're going to have access to it. There's going to be questions about security and privacy that we need to understand as a community. All right, a few more challenges, and these, I think, even lean more so into the research requirements they have. First, you know, process technologies continue to improve. It's great. If we're getting to gate-all-around processes, this would be great, but that's going to present new challenges, right? Backside power rails. All right, well, that really impacts our ability to you know, look at these parts, right? Our ability to probe, to look at these parts, it's just totally changed, right? If we have parts now, systems, potentially SoCs that have parts from multiple partners, how do those all come together, right? How do we make sure they're all tested the same quality? How do we, you know, do test? How do we debug between them? And then the other thing that's just been great, you know, one of the things that's enabled this change in the chiplets is the packaging technology. So it's not just chiplets, but that packaging, and it continues. It's just amazing how many things have changed. You know, it's just, I've been in presentations where we're talking, you know, up to 12 or 15 different possible package technologies coming up. It's just amazing, the proliferation of packaging techniques. And then the other thing is the requirements are changing too, right? If we're really looking at, you know, things that are like self-driving cars, you got these large data centers, which I'm sure you've heard about, you know, how big they are, and we heard a talk yesterday from Shriram on that. Just how big they are, and so in order to run a job for a long time across all of those, the quality needs are super high. So this is where we need research. I think this is an important thing for the community, right? Are there new fault models that we need to address with these new technologies? You know, do we need to have signal integrity inside the die or inside the package, right? What kind of standards do we need for the chiplet? You know, what kind of tests should we have that maybe are portable? And that's, I mean, that's especially important when you have multiple partners, right? Tests come from that partner, go into the next level. What kind of in-field monitoring do we do? So all this is things that I think are opportunities for the community. All right, so I said we'd talk a little bit more about these small delay faults. And this paper is actually being presented this week, so I won't go into too much details, but we've been working with MIT on some ideas of how we address this problem. And one of the key concepts in RAS is the idea of architectural vulnerability. So architectural vulnerability, you know, I like to think of it, a simple way to think of it that I think might help for those of you not familiar with that term, is, you know, when a soft error hits and you have a bit flip in your cache, if you have a bit flip in your data cache, you probably now have a data error. So you have to take some kind of corrective action to fix that. That is a highly vulnerable area. If you have a soft error and it hits in your branch prediction, what might happen is you take the wrong branch, but then you realize that later and you go back and take the correct branch. Not as architecturally vulnerable. So that's, in a nutshell, kind of the concept of architectural vulnerability. How do you assess what parts of the design have what kind of architectural vulnerability and then address that? So we've been able to think and rationalize this for soft errors. The question is, can we do that same process for small delay faults? Can we come up with a way of rationalizing this? And this is an area I believe that's prime for active research. We've worked with MIT. This is a very good paper on how we've thought about it. And I also wanted to point out that one of the things that is interesting about it is we're also leveraging DFT, right? The path delay fault model is part of what they're looking at to identify these paths, right? And the basic idea, I won't walk through it too much, but basically, when you have paths that have less slack and then they get hit by a small delay fault, they're more susceptible to this. So how do we identify those? So this is a very good paper. I actually am not going to try and walk through all of the details of it, but I wanted to put it forward as an example, just of one, right? I'm sure there's other examples of where we need more research, okay? And help us identify where to take action in the design phase. All right, so I just went through that. Hopefully you all have thought a little bit about, what does it take, how much we need to improve quality every year. The answer I usually give when I ask my engineers, how much do we need to improve productivity every year, is I point to Moore's Law. I said, we can't continue to have the same number of people per transistor. If we did that, we'd just be exponentially growing the size of the team, right? We need to be improving at a pace where we can keep the number of resources, both it's just so hard to have large organizations, and also it's great to be able to do things in a more productive manner. So we need to stick on the Moore's Law. However, where we're at now is we're in and I talked a little bit about this earlier, it's not just Moore's Law, right? There's also now chiplets in these things, and then the size of these is bigger. So if you talk about quality, I think quality is on even a faster pace. I don't have a specific number for you, right? It's something I think to think about, but our quality needs to grow at an even faster pace than the scale of how we're building these designs because of the critical industries we're going into, the scale of which these systems now operate, and the dependence that the public has on these. It's just vital that we increase that quality at a tremendous rate. All right, so now we're going to talk a little bit about the development phase. And here, I'm really going to talk mostly about testing. I'm not going to really talk so much about design and implementation. Those are also important, but today we're going to focus on testing. And the question I have for you all is, how much testing is good enough? Do we know how much is good enough? So a year or so ago, we were in a design review, and we'd made great strides on our coverage, and we appropriately gave everybody credit for that and said, hey, really appreciate what we've done, and we'd even given them more faults to go after. We'd increased their fault universe with new fault models. So they did a tremendous job. But we also then said, okay, well, what does that leave us? Even though we've done this, the percentage doesn't matter in this case, but we did. We looked at it, and it was a really large number. And that's what we're seeing, right? The fault universe is just exploding. Right, as we go through these technology nodes, we put all these silicon into an SoC. It's a humongous number. So, the question is, hey, is 99.9% coverage good enough if you have 10 billion faults, which we're going to get close to very soon, if not already past that in some of our designs? Is that adequate? Well, the problem with that, and I'm sure you already did the math and you've been thinking about it, is that leaves us with a lot of untested faults. And that's an area for us to start thinking harder about. How do we rationalize about those untested faults? Is there some way we should be categorizing those faults, identifying the level of risk on those faults, doing something to make sense of those faults that are left? And unfortunately, silent data corruption, I think you heard about that yesterday. You probably heard about it in a couple different slots. But it only takes one. Only one unfortunate of all those untested faults to then cause a silent data corruption. So, I'm not saying that we have 1 million untested silent data corruption, so please don't take that away. But it's still a problem we need to solve. All right, so when you think about coverage, you know, the problem just continues to grow. And we could talk about how many nines, right? It's one of the things we talk about, you know, is 99.99 or 99.9999. How many nines do you need, right? So I think the question starts to become, what can be done to achieve 100% coverage? We need to start thinking about that as a serious question, right? And then as I mentioned, how do we quantify what's not covered? So if we can't get to that 100%, how do we evaluate that risk that remains? What do we do to make sense of that so we know what the defectivity is for what's left and what kind of actions we need to take to get some additional coverage for that, right? And the other thing I didn't really talk about, this is just faults themselves. Some of these faults, you have to put the part into a certain test condition in order to actually hit it. Sometimes you need that to be on that part that's been thinned down so you could stack it on top. So now it has a thermal gradient across there. Now you need to have the logic that's actually exercising the path where there's actually a small delayed effect on there, right? And not only do you need to do that, you need to have done a DIDT event, a localized DID event. A global one that brings the supply down for the entire SOC, a local one that brings it down. You need all of these things to hit that fault. You know, that's a complicated scenario. But the question is, how do we find these things? And it's across not just once, but across the possible conditions they could fail. All right, so let's talk a little bit about testing. And you know, I think one of the things that I think I probably made the mistake of earlier in my career is to think, you know, some things were pretty well understood, move on to the next thing. I think we continue to find that there's so many things that it's better to just be curious, to think about, hey, what's something that's maybe been a standard, an accepted technique, but maybe it's time to be questioned. All right, so we're going to talk a little bit about burn-in. We're going to talk about structural tests and things that we need from structural test. And then we're also going to talk about the role of functional test. So one of these things that I thought was really interesting to learn in the last few years is that, you know, we've for a long time been able to do burn-in by loading things up in the scan, shifting things around. We can see the coverage we have and how many nodes toggle and stuff like this. It was great. But at some point, you know, it dawned on a few of the engineers in the team that, wait a minute, are we really getting that field effect across every device in the circuits that we have? And maybe we need to actually start thinking about it that way. Not so much that all the nodes toggle, did we get high coverage there, but did we actually get an appropriate field effect across every device? And then as we started looking into this and working on this, you know, this is not a simple problem. I believe there are some companies who have thought hard about this, but as an industry, I don't think we've, you know, have a good way of saying, hey, you know, you need to do coverage analysis of your burn-ins where you get field effect across every device. And there's questions there. How long does it need to be there? You know, it's not just did you get it, but how long? You know, what's the duration that matters? So I think there's some interesting questions there. Structural test. We all, I think, are familiar with this basic concept that, you know, there's just exposure to a number of faults that we need to have, right? And we've tried for many years to use structural tests to try and eliminate the need for system-level tests, but we keep finding cases where we just know they're different environments. When we are subjecting a part to structural tests, which is great for the amount of things we can test in a short amount of time, but we cannot duplicate that electrical environment entirely that a part will have in mission mode. And trying to figure out how to correlate those two, it's still something I believe we're working on. The other thing is you know, we also have the various phases of which you have testing, right? So this is, you know, we talked a little about structural, it's about functional testing now. So we complement that structural testing with functional testing. But here again, it becomes a question of how do we figure out what to run? Right? In an ideal world, we would know, if I go back to what I was talking about before, we'd know what part of the fault universe did not get covered by our structural test. Then we would run functional tests that cover that section, right? And we would actually potentially grade our functional tests by how well they hit those, right? So we get that complementary thing. And maybe identify the structural tests that really are susceptible to the electrical environment, and then those need to be tested with a functional test. And how do we get that coverage? I mean, it's a very complicated problem, and you know, it's not only, unfortunately, it's not only that we do this once and we test it, even if we could solve that problem perfectly. The problem is, as you all know, silicon degrades. So once it gets out there, what's not to say that, when do we need to test it again? And how much of it do we need to test again? And that's where, you've heard this conversation about ripple mode and, taking parts offline when they're in field, maybe do software update. We can give you a brief amount of time to retest the part. But also, how do we have tests that happen, that get scheduled like any other piece of firmware that goes in and tests the part? All these kind of concepts. But the question is, what's good enough? What's good enough to achieve this? We have worked with the University of Athens on this. This is also another paper that's published, and like the other, I recommend that if you all are interested to go check it out. But it's the idea that we need to have functional tests. And how do we craft functional tests that go after certain hardware and specific fault models in an automated manner, right? So that we can quickly create these tests and do this. So this is a great piece of work that we've seen from the University of Athens, which we've partnered with. If you're interested, I recommend you do it. It's showing some great promise, and we're hoping to see that and others continue to expand out. All right, so the question here was, what's good enough? What test coverage is good enough? Right, so first, can you cover the whole fault universe? It's a tough problem. Second is, do you cover all the faults under all the appropriate test conditions? And the third is, how often and how much do you have to retest over the lifetime of that part? Those are very complicated questions. When we think we can answer all those, that's when we know when test is good enough. All right, last section is about in service. Once a part goes through and it gets into service. And I'm going to talk a little bit about field learning, critical thing. And the question here is, how fast do we need to learn? And also, how do we measure the efficacy of a test? So we all know cycles of learning can be long. If you look at these, parts can be in service for years, right? It's amazing how long some of these parts will be in service. And it can take years to define a part and get it, to fully develop, to do the design work, get it through test, and get it out to the field. Okay, so these are long cycles, and you can see that they're a pipeline, right? The pipeline of these things happening. What's really good is if you learn something when you're in the correct phase. You're in the definition phase, like, there's a problem, and you have time to actually fix it. That's great. Or if it's out in the fleet, we talked about things you can fix in the fleet, various availability things I talked about that you can fix. That's great. And sometimes there's ways you can fix a problem with is like a software patch, right? So there are things we can do. You can do things quickly there. It gets more complicated when you come across something and you're already past the definition phase of the next product, or you're in the middle of it, or you're trying to catch not the next one, but the one afterwards, right? That becomes problematic. Now you have a problem that might be there for a couple generations. It even gets worse once it's already in service, right? Now you have something and you learn something, and it's maybe a great finding, but if you're past the definition phase of a program and it's nearing launch, and the next one's already through the definition phase, these things can be really hard to intercept. So what we need as an industry is to be able to move fast, right? And I've found that this is like a fundamental tenet of engineering, right? It doesn't matter which organization I've worked in. I've worked in verification, I've worked in physical design, I've worked in tests, all these things. The basic idea is how fast you can learn, how fast you can get to the time to a failure, how fast you can debug that failure, how fast you can take corrective action. That all affects how fast you can improve the quality. Right? Some people might say it's how fast you can improve the time to market, but I think the more important thing is how fast you can improve the quality, because once you get to a quality level, and we can talk about what that is, we can argue about it, you can then release the mask. And once you get to a certain amount of quality, then you can move it to production. And then your customers will be happy if it's a certain amount of quality. So I think it's the time to quality that matters right here. And the way we do this, the way we improve these cycles of learning is we share data. Like I mentioned before, there's complications here. Complications we're going to have to figure out as an industry because there's lots of data we'd like to have, but we got to work through those privacy and security issues. Getting the root cause, that's always fundamental. You can't just, we got to make sure we understand these issues. And sometimes that takes a lot of time, a lot of energy, but we got to get the root cause. The ability to see these issues is important. So sometimes just the ability to detect them is vitally important. And I've already talked about the time to debug. Now that's vitally important. That time to debug will affect our time to quality. All right, and then efficacy. Now this is something that we've seen and we've talked with multiple customers in the last few years. And they all have their own framework of what's an effective test, right? Which is fine. Everybody has their own needs. But it's really left us to reflect on, what is an effective test? And I think that's another important thing for us to consider, is how do you place a value on every test that you have? And how do you think of that value in relation to the other test? Does that value of a test change based on what the mix of tests are? I've seen cases where, we've put a test in place, it's captured some failure mechanism, it's done a great job of doing that. But then later, a couple quarters later, you're in a review of what tests they're going to do to help, improve the throughput of products, and they're like, this test hasn't failed in 2 quarters. All right, so how do you make that value statement? This test was phenomenally, important to catching some outlier, but now it hasn't caught anything for a couple quarters. How do we make that value statement of the value of that going forward? So there's been a number of ways people think about the efficacy. The number of bad parts detected versus other tests, how fast, the time, the latency to get to a bad part. This test got there much faster than this other one. You could think about how much cover it has of the fault universe, or you could think about the number of conditions. And this really is just a question I'm leaving to you, right? Is we need to improve these metrics. If we are going to get those cycles of learning I was talking about and get time to quality fast, we need to have really good metrics upon which we build those things. So, in short, kind of what I've tried to talk about today is, hey, first, we need to have a high quality end customer experience. We need to continue to maintain that. We need to maintain that all the way through the public, right? And to do that, I believe that there fundamentally are 3 key architectures. There's others that have a good part, but these 3 are important for the quality aspect, that RAS, that test, and that debug. Talked a little bit about some of the areas of ongoing research. Hopefully that motivated some of you, and hopefully that'll help us, hey, why do we need more junior engineers and stuff? We'll continue to invest there. We also need to continue to improve our testing. I think there are so many new ideas out there, new learnings we have. We need to continue to grow there. It's a great opportunity to be in this business and to be part of that. And then lastly, for us to succeed at this, we got to improve those cycles of learning and understand how we're going to measure efficacies of tests and place a value. I think you got to be able to place a value on tests, so when you make a decision, you can make a value call. And this community is just really part of that, 3 parts, if you will, that are required to build this trust and to have a strong ecosystem to continue to develop parts and continue to grow and have more computing everywhere throughout the world. With that, thank you very much.
Thank you. Excellent talk. We have time for questions. If you want, you can come to the micros there and there. But I will break the ice with a first question. You put a lot of emphasis on functional testing, and you show that apparently the best effort is coming from university. You mentioned University of Athens and the Dimitris Gitsopoulos group. So I'm asking myself, is the industry EDA companies are looking into that problem seriously. And yeah, is there's any plan to have tools to create programs automatically, for example?
All right, well, that's a good question. I won't try to speak on behalf of the EDA tool industry. I think that would be a mistake. But I do fundamentally believe that we should be looking for opportunities where it's for research, right? And I think we've found, and I think for a while maybe not all of us, but some of us have been in the mindset that, hey, we just need to keep working on the structural test problem and reduce the need of functional tests, because it's costly, right, to put these things in the systems, right? So there's a very strong economic pressure to get rid of that. But I think we continue to find that we need it to get to the quality level. And if we're going to continue to have it, we now need to invest in doing it well. And doing it to not only do quality, but also do it in a costly manner. So yes, and that's why I think we need to lean into some research. We need to lean into improved EDA tools. We need to continue to, we have people inside the company that strive to do this, right? And we need to encourage more of them to do that. It's a ripe field, I believe.
Thank you. No questions? Don't believe so. Oh yeah, we have one from Peter.
My name is Peter Maxwell, and I think I have more of a comment than a question. It relates to your question about what coverage is good enough. And what I think is an equally, if not more difficult question, is to add to that the notion that coverage represents fault models. I think the question is, how well do these fault models actually represent the real defects that occur in the circuits? Because faults don't occur in circuits, defects happen. So I think it's a very difficult question to answer. Even if you get 100% coverage, that isn't 100% of all the defects. And how do we answer that question?
You are absolutely correct. I was supposed to actually mention that. But yes, it's not only the full fault universe, but the fault universe do we actually understand the fault universe, essentially your question, right? Are there other faults out there that we don't have in our catalog that we need to address? Absolutely.
Hi there. So Savita Banerjee. So it would be great to understand, because I think we have this correlation problem in understanding the effectiveness of tests and when, and you expressed it beautifully. What data do you have to share back with us in terms of all the wealth of, you've got things in volume, you have the capability to do structural and functional, and to be able to do that cross-mapping of things? Is there something that the greater universe can benefit from based on the volumes of data that I'm sure companies like yours
it's a fair question. How do we share that information with the community? It's something I think we've thought about, we need to think more on. We are trying to collaborate, not as much with the universities at this point to kind of make that published information public. There's some issues to work through, and we got to be sensitive to those, but we do want to find a way to share information. But we do try to share it with some, where necessary, with our EDA tool leaders, so we can improve the EDA tools. And then we try and share it all the way through our supply chain, right? So as we start to look across the entire supply chain that we have, and we have partners on that supply chain, and that includes potentially all the way to customers, can we stitch all that data together and then look across all that data to make sense of why a failure happened, what test was effective, and it helps also to root cause. I think you're spot on. At a high level, we need to find a way to help share that information, do it in a manner that it allows research and development to happen, and learning to happen, but we'll keep working on it.
Hey, Steve. Regarding the cycles of learning, so you mentioned we're finding issues at different phases of the product lifecycle, and those observations are being found by different teams and different organizations, right? And so not only as you talk about challenges of learning across the industry, but within even a single company, of tying all these observations, if it's yield attainment or quality, or burn-in observation, or customer returns. And I think one of the challenges is getting all that back into the right hands to influence the next development cycle. So do you have any thoughts on what we can be doing better to speak the same language across different teams and organizations?
Yeah, well, this kind of comes down to what I'll call a basic engineering problem, which is true of verification and other things as well, right? First of all, one of the things that I've seen is a lot of times we all do things in our own localized databases. And there's the structural problem of getting the information from one team to another. So I think that's one of the areas. And that's, if you're going to look, as you look at this world now, we try to get to ML and AI, even basic ML. The data has to be presented in a manner that it can consume it. If it's got to understand 15 different formats to do this, you're spending more time on data conversion and trying to understanding than you're actually on data analysis. But I think, it's a tough question, right? But I think it's slow. You kind of build the processes to put in place. It's like, hey, if we're seeing a yield excursion, what does that tell us? Is that something that really is an indicator of something further upstream, right? It's not just, hey, wow, this test's starting to fail more and it's great we caught it. Also, is there potential that there's some risk and it's missed through there? And I think those kind of things need to trigger the appropriate process. And we're learning what those are, I think, as within the company. I'm sure it's even outside and across company boundaries of when this happens, what process step do you take? How do you build a process that is a continuous improvement process and always tries to drive that back upstream? Hopefully that helped a little bit with your question.
We have time for one more question, I think.
Mehul Shah of NXP Semiconductors. Thank you for a very enlightening talk. Can you share insights on how parametric testing and testing for mixed signal IP needs to evolve as we move forward, given the increased complexity of those circuits on modern chips?
Wow. Yeah, that's a tough one. Well, how about we chat about that one a little bit offline? Fair enough. That's not a 2-second answer, 1-minute answer. Very good.
Okay, then I think we can enter the break now. And thanks again, Steve, for the excellent talk. Very good. Thank you very much.